Last part of this lecture, we will discuss about the stability. So based on these G and CB, where G is the center of gravity and that CB is the center of so based on their relative position, we can have the equilibrium or stability here. So that CB is G. Okay. So in this case, even if you move, even if you tilt that, like for some reason it is tilted, these two forces, they will make a clockwise moment to stabilize this situation again. Okay, so that this case, that will be a stable equilibrium. Now for some reason, if the G is above the CB, now this case for GB, the weight is going downward, F is going upward. So in this case, they will create moment in this direction. So that will make the whole situation more unstable. So this type of case is the unstable equilibrium. The best one is the neutral equilibrium. The weight on the end of the bar is removed. So the weight and the buoyant force are balanced here. Any rotation of the submerged bar, like this one here, will cause it to remain in the newfound equilibrium position. Okay, so this one is the neutral equilibrium because CB and G, they are same position. Okay, so it will obviously depend on what is the loading and how much fluid has been displaced by that bar or the loading. Okay, now here we saw that if the G is above CB, it is unstable. But for some floating bodies, still they will be able to maintain the equilibrium even if the G is above the CB based on how the whole thing is set up. So O is actually where the water surface here and the line, connecting line between G and CB. So O is the intersecting point here. Of water surface or fluid surface and the G and CB. Okay. Here, what will happen if the ship undergoes a slight roll around this point A? So what will happen? A new center of buoyancy will be established because is addition of ABO area and subtraction of OEB area. That means there is a little bit rearrangement here, and that's why obviously the CB will be changed. Now here in this case, what will happen again? These two W and F, they will again create the clockwise moment and they will stabilize the whole situation. Okay, and M, this M is called mirror center. Okay, which is the intersection of this if the buoyancy force and the center line of the ship, like this one. Okay, now what will happen? For some reason, G is above the M point, like when it's heavily loaded, obviously G can be higher than that M. And in that case, if you look at this one, we have F, E, and W. So they will make a counterclockwise moment and they will make it more unstable. That's why it's very important when the maritime engineers design ships so that their centers of gravity are as high as possible without moving about M. Okay, the further G and M are apart, like these two, the greater the restoring moment will be and the faster the rocking motion of the ship will be. Okay, now let's do a very quick calculation. It's not calculation, just to understand the concept. So this is a wooden cube of 2 by 2. A vertical force F is applied at the center of one of its side and pushes its edges to the block of the water surface. So it is held at an angle at 20 degrees. Okay, so that was the initial one, and the tilted one is the one after applying the force. After tilting, center of buoyancy's location is, like after the tilt, obviously it is displacing different amount of fluid, so CB will be changed, and now this location is X is 0.09 and Y is 0.0832. Okay. Now they're asking, do you think the block will be in stable equilibrium when the F is removed? Okay, so when the F is removed, like this is the position right now. So here, that was the center of gravity, which is 0.1 here. So from this current situation, G is above the CB. And if you look at the situation, this force is going downward, this force is going upward. Eventually, they will make a clockwise moment. So yes, they will be in a stable equilibrium position when the F is removed. Yes. Okay, so that is the end of this class lecture. Now you should take the quiz, and that will be counted as your attendance. Thank you.